All right, students, let's go through the exam number 3. I'll start here with the part 1, the multiple choice questions. Let me jump right in here. It says a venturier tube may be used as an inlet in an automobile carburetor. If the 2 centimeter diameter pipe narrows to 1 centimeter, what is the pressure drop in the constricted section for an airflow of 3 meters per second in the 2 centimeter cross section? And then we also have the density of the air. All right. So with that in mind, maybe I'll need a little more calculating space for this one, because a venturi tube kind of narrows down here. And this is where the flow picks up. And so we have a 2 centimeter diameter here, a 1 centimeter here. And since the same amount of air that goes here has to go through there, it speeds up. And so when we did our little volume calculation, we said if you took the area here, call this area number 1, times the velocity at number 1, it would equal to area number 2 times the velocity at number 2. And they gave us enough information for the areas and one of the speed, so we can find the other speed. And let's see, they gave us the speed in this section. So if I look at the area here, this would be pi times r squared, which would be 0.01 squared. And then the velocity would be 3. The area, cross-sectional area in the narrow part would be pi times 0.005 squared. Let's see, 1 centimeter cut in half, good. And then we would have V2. And so my first step here is to find out what V2 is. And I can drop off the pi's. Grabbing my calculator, 0.01 squared times 3, and move this over, 0.005 squared, and I get 12. And so 12 meters per second is the speed there. So that's the first part of this problem. The next part, though, so I guess it's two-parter, maybe a little bit of a harder problem, is Bernoulli's principle. It says then if you take the pressure at some point, and I'll call it the pressure density or the pressure energy density, because then we have the rho g h1, and so the gravitational potential energy, and then the kinetic energy. All that then flows over to here, so there'll be a pressure 2, there'll be energy in its height and energy in its speed. And, of course, the venturi tube is held horizontally, so there's no increase or decrease in gravitational potential energy. And, of course, the reason it flows faster here, besides the fact that it gets narrow, but it gets its energy to flow faster from a drop in pressure. And so it gives up some pressure energy and gives it to kinetic energy. So the lower pressure should be here in this venturi tube. So let me write this as P1 minus P2 so that it's a positive number. And so this is going to come out to be the 1/2 rho, and I'll go V2 squared minus V1 squared when I move this, and then factor out the 1/2 rho. And now I can put this into my calculator, 1/2 times rho, 1.2, times the quantity. And velocity number 2 is 12 squared, minus velocity number 1, 3 squared. Should give me a drop of about 81 psi. So, not psi, pascals. I did everything in kilograms, meters, and seconds. So that'd be answer E there for the first one. Yay, hope that made sense. All right, let's go on to the next one. So the next one says the pressure difference, delta P, drives a fluid with a velocity, drives a fluid that has a viscosity of 1.25 through a round tube, and it gives its radius and its length. What is the flow rate? All right. So for this one, probably best that I kind of open the book here. Let me see if I can find the book. Oh, I had it open. A bummer I closed it here. Let's see. Online, go to the book. Fluid. We're at the beginning part of the test, so we're doing the fluid dynamics here. But we're doing our laminar flow, assume a laminar flow. And so what section? I'll just, let's see, call out. I got this listed. Does it list the section number? Yeah, 12.4. Okay. And Poisson property is somewhere in here. Here it is. Where it lists a connection. There it is. That the flow rate, Q, is the pressure difference. Actually, your book lists it as P2 minus P1. So we're going to use up some of our energy, depending on the radius of the tube to the fourth power and the viscosity and the length. And so you can see that the higher the viscosity or the longer the length, the lower the flow rate is. And of course, the bigger the flow rate is, the bigger the pressure difference, because that's what's pushing it through, or the radius, okay? But what we're after here, the pressure difference drives a fluid of viscosity of through a round hole. What is the flow rate? So we're after Q. So there's a pressure difference of, is that a 2 or a 2.0? That's 2.0. So 2.0 pascals. We've got a pi. We got a radius of 0.1, raised to a power of 4. We got a viscosity of 1.25. And we probably should check our units. That's meters, that's Pascal. Okay, that's Newton meters squared. Okay, so they're all in the SI base units, and a length of 0.4. And so maybe the harder part of this is recognizing what kind of problem it is. If I go 2 times pi times 0.1 raised to a power of 4, then divide that by 8, also divide it by 1.25, also divide it by 0.4, I get a flow rate of 1.57 times 10 to the minus 4. And it must be that one there. Nice. And so I guess that would be A. All right, let's move on to number 3. So number 3 says a building that's, let's see where to go here. A building made out of steel is 6.5 meters high on a winter day when its temperature is 0 degrees Fahrenheit. How much taller in centimeters is the building when it is 100 degrees Fahrenheit? Oh, and then it gives the linear expansion to it. All right, so I'll go ahead and say, let's go ahead and write this. Delta L equals to alpha L naught delta T. And actually got me thinking that maybe I should, let me check the book here. Where do you guys do the thermal expansion? Because I think the notation might be a little different. This has got to be from chapter 13, linear expansion, yeah, so 13.2. And, oh, that is the same notation you guys use. Okay, good. All right, so I'm going to go ahead and then put my alpha, 11 times 10 to the minus 6, and it is inverse degrees centigrade, or Celsius. Now, the reason that's important here is I'll put this in meters, but that also means my change in temperature needs to be in Celsius. And they give it me in Fahrenheit. So let's be a little careful there. Maybe I'll do that on the side. You can get the temperature on the Fahrenheit scale by taking Celsius, multiplying it by 5/9 and adding 32, which if I do the reverse math means Fahrenheit minus 32 times 5/9 is temperature in Fahrenheit. So putting it, Celsius. So you can put in your 0 degrees and your 100 degrees. But it's probably better just to remember the 5/9 because then the delta temperature on Fahrenheit multiplied by 5/9 is going to be your delta T on the Celsius scale. So I'm going to take that method, just not worrying about the offset of 32. And so this would be 100 change in Fahrenheit. And then 5 divided by 9 means it's going to be a change of about 55.6 degrees Celsius. So that I'll put here. So then if I multiply that by the 650 and multiply that by the 11 times 10 to the negative 6, I get a 0.397. And of course, this is meters. So that's rough. If I round it, the 40 centimeters, we're looking at our answer for number 3, which would be a C here. Okay, good. All right, so there's the first 3, if you will. Number 4. A bubble having a diameter of 1 centimeter is released from the bottom of a swimming pool where its depth is 5 meters. What is the diameter of the bubble when it reaches the surface? The temperature of the water at the surface is 20 degrees Celsius, and it was 15 at the bottom. And so one of the things we're working on a lot here is this PV equals nRT. And the bubble then is going to change its pressure and its volume and its temperature. But it's not going to change its number of molecules. And it's, for that matter, R is a constant. It doesn't change. So I could say this is, I'll call it number 1 down at the bottom. And then at the top, let's call these all number 2. And so it goes out to the top. It's got new pressure. It's got new temperature. And it's going to have a new volume. And that's what the question is asking. Well, it's actually asking for the diameter of it. So we'll just do maybe the volume part of this first. I will have to do a kind of a side calculation here with the pressures. Maybe I'll bring this paper back into play here. Maybe I'll get a fresh sheet, because this will take us back to the previous chapter, which I think is chapter 11, where the pressure at the bottom of the swimming pool would be the atmospheric pressure plus the rho GH. And so I'll call that pressure at the bottom, number 1. Pressure at the top, though, is just atmospheric pressure. So I could take this as 101,300 pascals for pressure number 2. Okay. And pressure number 1 is then going to be this 101,300 plus this rho, and so it's water, so that's 1,000, G 9.8, and a depth of 5 meters. So grabbing my calculator here, 1,000 times 9.8 times a depth of 5 meters means that this part is going to be an extra 49,000 pascals of pressure. Added to the 101,300, and this total then is 150,300. Okay, so there is pressure 1 and pressure 2. And the same thing can be said about the temperature. The temperature needs to be on the Kelvin scale, so it's 273, and at the bottom plus 15. And at the top is 273 plus 20. I guess that makes it 293. That's pretty good. And then that's just 5 short of that. So is that 288? All right, 882. Yeah. Okay. All right. So now I have the two temperatures. And for the volume, I know the volume is 4/3 pi r cubed for a sphere. Maybe I could write that as 4/3 pi diameter at the bottom, cut in half, cubed. And I think I will. Well, that's going to be volume of number 1. And then I will know everything to get volume number 2, and then I can reverse back to get the diameter. So let me get the volume here. Volume would be 4 divided by 3 times pi times, and the bubble has a 1 centimeter. Let me just write that as 0.005 for the radius cubed. Okay. And so this is going to be 5.236 times 10 to the negative 7. Sorry, 7. Okay, so putting all this together as P1 V1 over T1. Let me just do that. So I already have the V1 in my calculator, so let's go times. And then pressure number 1 is this one up there, so I'll just copy and paste that. And then divide by temperature number 1, which is 288. So all of this is 2.73 times 10 to the negative 4. And again, that's supposed to equal pressure 2, it's 101,300, times volume 2 over temperature 2. And temperature 2 is 293. So taking this number and multiplying it by 293, and then dividing it by 101,300, I'm going to get a volume of number 2 of 7.90 times 10 to the minus 7. And of course, that's supposed to equal to 4/3 pi r number 2 cubed. So if I move the 3 over, that'll be times the 3. Move the 4 over, that's divide by a 4. Move the pi over, that's a divide by pi. That should be the radius cubed. And then raising it to a power of 1/3 should give me the r. Multiplying that by 2 should give me the diameter. And so we're looking at a diameter of 0.0115. And I did everything in the base unit, so that's meters or 1.15 centimeters. I hope that's a choice here. 1.15 centimeters. Answer is B. Okay, good. All right. Some good calculations here. All right. And let me get ready here for another calculation. Well, it looks like the next one isn't a calculation. It says here, for an astronaut working outside in the space shuttle, so they're in the vacuum of space. That's going to be an important part here. The greatest loss of heat occurs by means of, well, it can't be conduction or convection, because conduction and convection involve molecules, and in a vacuum means no molecules. So things in outer space like satellites and space shuttles, and in this case, an astronaut, needs to get rid of their heat by radiation. That's the only way they can dissipate heat. I was going to say that I'm not sure. I mean, you could run because they're attached. But if you're by yourself, you could. I mean, if you by yourself, you'd have to be radiation. So a satellite by itself, or the whole International Space Station. But they do run these cooling tubes down the tethering and run it through and back. And so that's the ability to keep you warm or cool, is by circulating a fluid. Anyways, but the intent here of the problem, I'm getting sidetracked here, is on the radiation. So should be C for number 5. All right, going on to number 6 here. It says the Earth intercepts about 1.27 times 10 to the 17 watts of radiation. I think that's a good number. Let's see if I tried to draw a sphere with sunlight coming in. And sunlight is about 1,000 watts at our location. And then imagine cutting the Earth like a tomato or something. It'd be a pi, a radius squared, and the radius of the Earth, about 6.3. And maybe I shouldn't take time to do this, but I am curious. That just seems like a really big number, but at the same time, the Earth is a big place. 1.27 times 10 to the 27. Okay, so a lot of energy. Solar power is got a lot of potential, and so that's a lot of power coming to the sun. And then it says, suppose that the Earth, which has a volume of this, and again, just out of curiosity, 4/3 times pi times the radius, 6.67 of the Earth cubed would be the volume of the Earth, 1.08 times 10 to the 21. Okay, so this would be like the whole thing is not, the whole thing is water, which obviously is not really what the Earth is. But if you're trying to warm it, instead of warming water, you'd have to warm rock. But anyways, what's composed of water. How long would it take for the Earth at 0 degrees Celsius to reach 100 degrees Celsius if none of this energy was then re-radiated or reflected back out to space? So obviously a lot is reflected back out into space and re-radiated. So in fact, ideally the same amount is, so that there's no net warming of the Earth. So a very hypothetical question, but I see the point here, and that is, if you're going to warm up water, maybe I'll get my little pad here. The amount of energy is Q equals mc delta T. And the mass would be the density of water times the volume. All right. So let's start with the density of water, which is 1,000 kilograms per cubic meter. So if we then multiply this by the volume, 1.08 times 10 to the 21 cubic meters, that first two pieces were going to give us the mass of this big sphere of water. Now, maybe I'm just going to do a little side note here on the specific heat, because I know it as 1 calorie per gram per each degree Celsius. And I also know a calorie is 4.186 joules per gram. And now if we multiply top and bottom by 1,000, the top becomes 4,186 joules. And multiplying by 1,000 will be kilogram per degrees, which is the same number I think you'll see in your textbook, if you look up the specific heat of water, it's like 4,000. In fact, I have the textbook here. I think we've transitioned here into chapter 14. Change of temperature capacities. Yeah, so section 2 of chapter 14 seems like the place to go. Yeah, and they have joules per kilogram. Where's water? Water. Yeah, there it is. 4,186 joules per kilogram for each degree. Okay, good. And since I did it from memory, but you're not expected to know it from memory. Just kind of look it up there in section 2. And so I have that number, which we'll put then right here, 4,186 joules per kilogram per each degree Celsius. And we are warming it 100 degrees Celsius. So degrees Celsius is going to cancel. Kilograms is going to cancel. And then that tells us how many joules is needed to warm up this big sphere, which isn't quite done with the problem, but let's go through this. So 1,000 times 1.08 times 10 to the 21 times 4,186 times 100. All right, so we're going to need 4.52 times 10 to the 29 joules. Wow. Okay, now, they told us this rate of 1.27 times 10 to the 17 watts. So that would be Q over T, or in other words, the time is the amount of heat you want to get divided by this rate. Okay. So we want 4.52 times 10 to the 29 joules. And we're going to be sending it in at a rate of 1.27 times 10 to the 17th. And I'll put watt as a joule per second. So you can see that the joules cancel off and the seconds flip and multiply. So take that number, divide it by 1.27 times 10 to the 17th. And we are looking at 3.56 times 10 to the 12 seconds. Okay, well, if we divide that by 60, we'll get minutes. If we divide that by 60, we will get hours. If we divide that by 24, we will get days. If we divide that by 365, we will get years. So it looks like 100 and I'll call it 13,000 years. Or, good. They write it as 1.13 times 10 to the 5 years. So I guess the answer is A, B, C, D. D is in dog there. Okay, nice. All right, on to question 7 here. 7 says, a 2 kilogram mass is attached to a spring of a spring force constant of 290, as in the figure. Okay. The mass is displaced from its equilibrium into a list. Its frequency in hertz is. All right, so the period is 2 pi over the square root of m over k. And the frequency is the reciprocal of that. So I'll take the mass and divide it by k, 290, and then take the square root of all that, multiply by a 2, and also multiply by a pi. So there's the period. Reciprocal of that would be the frequency, And so we're looking at a 1.92 hertz, and 1.9 would be the closest there. So that would be D. D is in dog. Okay. Now, finally, a shorter calculation. Did have 2 steps, though. Here's some wave motion. Write the equation for a wave traveling along the positive x-axis with an amplitude of 0.02 meters, a frequency of 440, and a speed of 330. And it looks like we've got different options. We know it's going to be one of the trig functions, and it actually wouldn't matter whether it's sine or cosine because they don't really say how it begins. And so, sadly, I can't really rule anything out quite yet. And in fact, maybe you kind of remember this discussion on the wave equation, but there's a couple ways of looking at it. It would be amplitude times either a sine or a cosine. Let me look at the book. I think we emphasized maybe one or the other. Let's see. Oscillatorial and waves, chapter 16. Here's waves, section 9. So 16.9 is my guess where the equation is. Next section, looks like. Or was it earlier? Because looks like they're using it here in section 10 out of nowhere. No, maybe this is where they derive it. Okay, so it must be in section 10. And it looks like they use cosine here. But I hope that doesn't throw you off because the sine and cosine are essentially just the same thing. But we could have, and like I said, kind of depends how you want to write it here. Oh no, that's superpositioning. Kind of looking for the general equation of the wave. I know it's somewhere in here. Well, I'm going to do both. Sometimes we write it as kx plus or minus omega t, and other times it's written, depending on the textbook, and I was thinking this is how your textbook wrote it, as a k times an x plus or minus a vt, because k times v factors out to an omega. And I'm not sure if your book went this direction or this direction. So maybe I'll just go the first direction. It's a little nicer, so I'm going to put A for amplitude, 0.05. And again, sine or cosine. But none of that's really going to help me here because as I look at the answers, they're all sines and cosines, and they all have the amplitude. So that is necessary, but it doesn't help me eliminate anything from here. But I do want to say this, then, that in order to travel in the positive x direction, here's the first real clue, is I need a negative sign. And so the negative travels in the positive direction, and with that, A is still good, B is still good, but I can throw away C, D, and E. They all have a positive sign. And so even if other things are correct, they would be traveling in the wrong direction. So they wouldn't be traveling in the positive x direction. So that's the real big clincher of this. And of course, one's a sine, one's a cosine. But they do have some very difference in here, and that's where we want to focus on. So let's go with the omega. The omega, the angular frequency, is 2 pi f. They told me the frequency was 440, so times 2 would be 880 pi. Now, neither of these have a direct 880 pi, But you can see here, because of the parentheses, this 880 pi right here, 3.14 is pi, needs to be distributed. Whereas this one doesn't have the parentheses, so it's not being distributed. So this couldn't be it. Which means by elimination, it's got to be A. However, it might be nice to also point out that K is 2 pi over lambda. And if you remember, velocity is lambda times frequency. So if I rearrange this for lambda, V over F is my lambda, I can write this as 2 pi, and in place of lambda, I could put V, and I'll flip over F. Because this is that omega again. So this would be the omega over the V. And as we just said, the omega is the 880 pi. And the velocity was given as 330. And I think that fits right here. Yeah, when you do the distributed, there's the 880 pi going with the K, and then divided by velocity. So it's got the negative sign. It's got the right coefficient in front of the X and the right coefficient in front of the time. And so, again, it works perfectly. So I guess it's A there for the answer. Nice. All right. Moving along here. Number 9 says what? Calculate the intensity level in decibels of a sound wave that has an intensity. So in decibels, sometimes using the symbol beta, would be 10 times the log of the intensity divided by what we call its reference intensity. Now this must be in the sound waves, so chapter 17, where does 17, section 3, I'm kind of scanning the book here, probably have, there it is, this equation. They have a beta, good, and then they have a parentheses for measured in units of decibels. 10 log, I do log base 10, okay. And so now I can just put in my numbers. This is 15 times 10 to the minus 4. And the reference intensity, which we call the threshold of hearing, is also given as 10 to the minus 12. And so now it's just a matter of punching those numbers in. So 15 times 10 to the negative 4. It's a lot of sound energy. Divided by 1 times 10 to the negative 12, a threshold of hearing. So it's a huge ratio. Take the log of that answer and multiply it by 10. And so 91, 92 decibels is what it would round up to. So I guess that would be answer C. All right. And finally then, the last question. Says we have a truck moving. So here's the truck moving this way at 36 meters per second. And now we have a police car at 45 meters per second traveling in the opposite direction. So they're approaching each other. Or, not a head-on collision, I hope, but this is in one lane, maybe northbound, and this is southbound. If the frequency of the siren is 500 relative to the police car, what is the change in frequency in hertz heard as they passed? And so hopefully a lot of bells and whistles are going off in your head about the perceived change in frequency called the Doppler effect. And we had 2 pieces of that. Let me see if I can do the same note, make sure I do the same notation that's in your book here. Doppler is section 4 of chapter 17. Your author calls this the observed frequency, is based upon the frequency of the source. Okay, and then we got the velocity of the wave, and then if the source is moving, you take the velocity of the wave and I'll write it as a plus or a minus, times the velocity of the source. And so this is this observed frequency shift when the source is moving. And if they're moving together, you use the minus sign. If they're moving away, you use the plus sign. And of course, there's another nice little equation. We're going to put the two together that kind of looks the same. It's just down here, they have the velocity of the wave, and then you have the velocity of the wave, and again, plus or minus the velocity of the observer. And this is what you will use when the observer is moving. And we've got both of those. So you might say the frequency observed when both are moving would be this first factor. And that's because the source is moving. And now you have another factor due to the observer moving. And what's nice is putting those two thoughts together. We actually have a simpler equation. In fact, now that I'm scanning your book, I'm looking here, and it looks like this is what I exactly did right here is what your author did on, I guess, equation 17.26. And so you're going to get the velocity, and you're going to have the wave, and you're going to have plus or minus the observer. And then in the bottom, you're going to have the wave plus or minus the source. And so that's the first step, I guess I would say, is incorporating a Doppler effect because both the observer and the source are moving. And the other part is keeping track of pluses and minuses, because if they're moving together, well, okay, let me just talk about the observer. So if the observer is moving towards the source, which it is, we do the plus sign. And if the source is moving towards the observer, we use the minus sign. So maybe I should do this. The observed frequency, and I'll put before they cross, would then be this 500 hertz. So there's the 500. It would be the velocity of our waves, which these are sound waves. So that's a 343 going here, and then also down here a 343. And then our observer is 36. And our source is 45. Okay. But like I said, as they're coming together, you would use the plus sign for the observer, but the minus sign for the source. Okay. And the same calculation would be applied to after they passed. So I'll go after. And you'll have the speed of the wave and the speed of the observer and the speed of the wave and the speed of the source, the police car. But now once they cross, the observer is moving away and the source is moving away. And so this is why you'll hear that change in pitch between as they approach and as they fade away. So as they approach each other, you're going to hear a higher than 500 by whatever this amount is. So let me just put 500 times the quantity 343 plus 36 divided by the quantity 343 minus 45. And so that's going to be about 636 hertz would be that frequency as they are approaching. Now, as they move away, we're going to hear something lower. So 500 times 343 minus 36. divided by 343 plus 45. And now we're going to be at 396. So if I subtract the two, so I'll take this one up here minus this one, and the pitch change is going to be, I'll call it delta F, about 240 hertz. Very noticeable. Very, very noticeable. And so 240 would be the answer C. In fact, so noticeable that, even young children playing with cars go, you stand here, they go zoom. It's like vroom. So they have a high frequency as it approaches and then a low frequency as it goes away. All right, well, I hope that helped. That's the end of the multiple choice. I'll stop this video here and then go over to the free response. Hope you did well.